Hey programmers, Alvin here. Right now I want to go over a JavaScript solution for this depth first values problem. And so what we're going to do here is really just implement that same strategy that we traced through in the approach video, pretty much to the T. And we'll start with the iterative version. And that means, of course, we will solve this one in two different ways, right? We're going to solve it iteratively first, and then afterwards we'll go ahead and solve it recursively. All right, so let's jump right in over here. Now, like we said in the approach video, we know that the iterative version really relies on us creating a stack. And for most of your programming languages, you can just go ahead and use your array data structure for that. So I'm going to use just a plain old JavaScript array. I'll go ahead and name this one stack. And we can just use an array to represent a stack as long as we stick to two particular methods, right? I'm going to use array push, which adds to the end of an array, and also array pop, which removes from the end of the array as well. So I'm going to consider the end of my array to represent the top of my stack. Cool. What I'll go ahead and do is initialize the stack with the root node on top of it. Nice. Then I can have my main loop for the algorithm. So we know that we need to keep running the algorithm while there's stuff on our stack. So I can just check while stack.length is greater than 0. So while I have at least one element on my stack, there is some work to be done here. And now we'll step through a single iteration of this algorithm. We know that we start an iteration by just removing the top of our stack, in other words, stack.pop. In JavaScript, that will also return us the element that we just removed. So I'll call that my current, const current. And that is going to be an instance of node. So it's going to be one of these objects. Cool. So now that I remove this element from the top of my stack, let's say for now, I don't know, print it out. Maybe we'll kind of debug this one as we go. So I'll console.log current.val, because I know that every instance of node has a .val prop on the inside. And then from there, I need to add this node's children. So you might go ahead and guess that to do that, we can just do stack.push. I'm going to push the left child. What's going on here? So node or current.left followed by the right child. But we also need to make sure that these children exist, right? If you look at the prompt, there could be instances, for example, like this C node over here. This C node only has a right child but has no left child, right? So what I don't want to do is push C's left, because then I'd be pushing null onto my stack, which would give me an error later on, right? So I want to only push the children if they exist, and I need to individually check if the left exists, then push it, and also if the right exists, then push it. So I'm just going to add some guard statements for both of these. So we'll go ahead and we'll insert, we'll say, all right, if the current has a left and right, so we'll say current.left, and I'll adjust this for the right-hand side. Cool, maybe we can inline this if you prefer. All right, so I'm going to only push the children if they exist. And that should actually be the heart of our depth first algorithm. So we're not putting our values inside of an array like the problem asks, but we should at least be able to see the correct order of printing here, because I'm going to print a node's value as soon as it is removed from my stack. So I'll go ahead and actually maybe bring in maybe one literal test case. So I could just steal this little stub over here, and this will just print out the values, right? So I'll test this. I can hit run. If I hit run, it's just going to execute this file just like a script. So it's not going to run any automatic test cases. It's just going to run my file as is. So if you want to test it in this way, kind of in a manual way, you're going to have to be sure to call your function. And I do have a console.log on the inside. So I'll just run this manually. And when I do that, I should see some output here. Looks like node is not defined because I forgot to bring in my class definition. So I'll do that. Give that a go. All right, so looking at our output, we didn't get our exact depth first traversal like we expected, right? I got ACF BED. If you take a look at what we really printed out, we technically did print out a depth first print, but we favored the right hand side. So we did ACF and then BED. So let's say we really wanted the left to right version of this. Now all you have to do is flip the order that you pushed the children, right? It should be clear by looking at these two lines, right? When I add my children, it looks like I push the left child and then the right child. If you push the left child first and then you push the right child afterwards, that means that the right child's going to be on top for the next iteration. So if you do it like this will favor the right-hand side and travel through it first. But if you did it like this, now you'd be actually iterating to the left branch first, toward the right. So with that small change, let's just see what our print is. And there I have a nice ABDECF. However, in this problem, they want us to actually return those values in an array. So I can kind of get rid of this little manual test over here. I don't need this class definition anymore. And now instead, I'll just gather up all of my values in some results array. So I'll say, I don't know, maybe a result over here starts as an empty array. And then as I pop elements from the top of my stack, instead of logging them, I'll go ahead and do result.push, and I'll push that value into the result array. Once I'm done with this while loop, that means my entire tree has been explored, in which case I can return, make sure you spell it right, return my result. Cool, so this should be a nice solution. Let's actually run the test cases on this. Give that a go. So it looks like we're doing pretty good, but for this very last example, looks like we're getting can't read property val of null, and that's running test case 04. So if you actually go into the prompt, those test cases are actually laid out explicitly over here. So I want to go to 04. Yeah, it looks like the 04 test case, they go ahead and they pass my function null, right? Kind of representing like an empty tree or an empty node. And we can kind of trace through what happens here for our code. Let's say that root was null. That means when we initialize our stack literally contains like a null value. So it's not even an instance of no, it's just null. So that means when I enter this while loop, I'm going to check, do I have anything in my stack? And I do, because my stack length is 1. And then when I pop the top element of my stack, current is going to be null. And then on this line 14, it says null.val. And that's actually where our code explodes right on line 14, right? You can't reference property val of null. And so to handle this scenario, we want to make sure that we actually never allow anything null to enter the stack. It's kind of why we had this guard over here. And that should also be true for even the top level root. In case they give us the empty tree, kind of seems like a corny, edge case, but this is a pretty common one when you actually go into your interviews, right? What happens when you have an empty input? And so I'll just guard that explicitly. I'll go ahead and check, hey, if my root, so if my entire tree is empty, so if root equals null, then what I'll do is just return an empty array, right? Because that means there are no values inside of it. And that actually is the expected answer according to this, right? Should return an empty array. So let's give it a go now. Should be pretty good. Nice, and there we have our nice iterative solution for this depth first values problem. All right, so here's what we'll do. That was one solution. Let me show you another way to implement this, and that would be our recursive flavor. So I'll just kind of redefine it down below. And I actually recommend practicing both versions because they're going to serve as like the basis for which you solve a lot of different tree problems. And so when I think about the recursive version, like all of our recursive code, I must think about the simplest case of my input, and that will act as my base case, right? So in the case of a binary tree, the simplest tree you can be given is going to be the empty tree or just a null root, right? So it's not even going to be about a node that's a single node, right, inside of a binary tree. It's going to be about an empty tree, right, a tree with 0 nodes. So I'm going to check, hey, if my root is null, then I have an empty tree. And I think about this base case as if it's its own input, because it really is, right? And so if someone asks me to give them back an array of all of the values in the empty tree, it's still the case that this must be an empty array, right? Because there are no values. There's not even any nodes in the empty tree. And then from there, I can generate my actual recursive call, right? And I know when I call my stuff recursively, that means I have to reference the function name again and go ahead and invoke it. And I'm going to call upon root.left as well as root.right. All right, so this call over here would give me back an array containing all of the values in the left subtree. And this would give me an array of all of the values in the right subtree. And so let's say I save these into their own variables respectively. You don't have to do this part, but I'm kind of a fan of it, especially if it's the first time you're implementing this. So I'll call this my left values, and I'll call this one my right values. And here is how I'm able to kind of quickly create recursive code. It's all about taking what I call is the recursive leap of faith here. So let's say we're stepping through test 0, 0. And so this is our tree visual, right? So we know that our root is going to be the A node. So when I actually make this top level call, this base case does not fire. And so I make my recursive calls, right? I know when I do depth first value, or values rather, let me fix that. Depth first values of root.left, that means I'm going to be passing in the B node, right? And here's how I have to actually pretend my code behaves. I'm just going to get back the correct result from this call, right? So if I passed in the B node into this call, what I expect back is the full array representing the depth first traversal of that subtree starting at B, right? So if I got correct data over here, what it would look like is just B, D, and E. Right, that would actually be the full depth first traversal from this subtree, right? And I'm kind of doing that just mentally, right? I know the expectation for this algorithm. It's going to be a similar story for my right call, right? If I'm at A, so A is still my root, and I passed in my right child C into this call, what I expect back is just an array of CF, which would be the depth first traversal of that left subtree. And now that I have, my left subtree values and my right subtree values, I have to think about how to combine it all together, right? How do I work myself into that output by combining both of the results from my children, right? What I need to do is really just take myself, put it in the array, followed by my left children, followed by my right children. So I can use some nice JavaScript syntax for that. I'm going to return a new array. I'm going to throw myself in there. So I'm going to throw in root.val. That's myself. So that'd be like the A node. Then I just take all the values in my left result, put them in here. I'm just going to use the spread operator to unpack that array. And I'll do the same thing for the right values of CF, right? So ... spread out right values, just so I return a single array. And this pattern itself does match this output, right? Kind of taking the leap of faith and assuming correctness from these recursive calls over here, right? I have A, then I plug in, substitute BDE, and then for the right, I have CF. Maybe before we run this, I'm not going to, assume too much JavaScript knowledge. So maybe you're kind of new to this spread operator. So in general, super quick aside over here. Let's say I had an array of some stuff. So I'll say peeps, throw in some people over here. So we'll throw in Felipe, we'll throw in Jason, throw in Raj, throw in Abby. And what I can do is whenever I have an array, I can just use a spread operator to kind of unpack that array. So for example, I can say const, we'll say new peeps, and I'll create a new literal array. So whenever I say square brackets, it gives me a new array literal. And what I'll do is, put an element at the front. We'll call it Alvin. Then I'll spread out the elements of peeps. Right? So just imagine I took all of the elements here and just removed the brackets. That way I don't add any initial nesting. And then at the end, I can add someone else like Brian. We'll console.log what new peeps looks like. So I'm not going to run the test cases. We're just going to run this file as a script just so we can review this spread syntax. So if I give that a go, we kind of make this bigger. Notice that I have correctly spreaded things out, right? I have Alvin at the front, and I have all of the things from peeps in the middle, right? Followed by Brian at the end. So you can do this. You can also use like the concat method on arrays. You're probably going to see me use this spread syntax a lot because I'm kind of a fan, right? But with that in mind, let's go ahead and actually test this code. So we'll run all the test cases. Nice, and this is another working solution for our depth first values. And it should be pretty natural that we can solve this problem also recursively. So I know that the iterative solution for this depth first traversal requires a stack data structure. And I know whenever I write recursive code under the hood, your programming language is actually going to track all those recursive calls using the call stack, right? That call stack behavior gives you the same type of ordering, which is really convenient. Cool. All right, so before I send you off on the next problem, I want you to actually practice both solutions for this depth first values code. It's going to be very necessary to actually master some later concepts that are coming right up. So do spend some time on this. Practice makes perfect, right? And I'll catch you in the next one.